We present film, a frame interpolation approach designed to handle large motion. Frame interpolation has been commonly used to upsample the frame rate of a video. More recently, frame interpolation has shown great promise interpolating between near-duplicate photographs, producing a smooth, high-resolution video of the captured moment. We propose a neural network architecture that can be trained end-to-end with image triplets alone. Our system works as follows. We start from two input images, I sub 0 and I sub 1, and the first task is to produce two feature pyramids. We start by generating image pyramids of desired depth. Here we show pyramids with 4 levels, but in our system we actually use 7. We use a special feature extractor that produces feature pyramids that are scale agnostic. In other words, they have similar meaning across different scales. The feature extraction starts by extracting a smaller pyramid of features from each image pyramid level. This is done here for the finest resolution. Then we run the same feature extractor on all columns. This extractor on each column is actually identical to a unit encoder. The same weights are being used in all columns. We repeat this process for all levels in the image pyramid. Once the columns are computed, we concatenate the features horizontally. This produces our final feature pyramid. Note that from the third level onwards, the feature stack is similar. This is the key to our method, as it allows weight sharing in the subsequent flow prediction step. Note that the feature extraction is done for both input image pyramids. Only one is really shown here. For flow estimation, we use a residual pyramid approach that starts the estimation from the coarsest level. Then, on each finer level, we compute a residual correction to the estimate obtained by upsampling the coarse prediction. A learn module predicts these residuals on each level, and shared weights are used on all except for the few finest levels of the pyramid. Once the flows have been estimated, we warp the two pyramids into alignment, we concatenate them together with the flow fields, and feed the results into a unit-style decoder. We call this stage fusion, as it fuses together data from both inputs and produces the final output. To train our model, we employ the style loss in order to predict sharp and pleasing frames at inference time. First, we extract the VGG19 features from the predicted and ground truth images using a pre-trained ImageNet model. Next, we compute the gram matrix at each level as the inner product of the reshaped features. The gram matrix loss is the L2 norm of the matrices, which matches the correlation of the features. Finally, our style loss includes the sum of the L2 norms at each level. In this ablation comparison, we see how the style loss greatly helps maintain the sharpness and contrast of the tree leaves and branches in the background. Our film model, shown on the right, produces temporally coherent and high-quality frames. It can preserve intricate detail, such as small fingers and sharp facial features. Film also compares favorably when interpolating across large motion. It can produce realistic inpainting in the presence of large disocclusions. Notice in this example how the picture frame on the wall behind the child's head is correctly revealed. Even with challenging scenes and large motion, film generates sharp images consistent with the inputs. Even though the image quality is high, some movements can sometimes look unnatural, as is the case under the feet on the left example and on the moving fingers on the right example. Here are a few examples of near-duplicate photo interpolation.